Okay, so we are going to continue our chapter on digraphs with the sort of second lesson, which is on connectivity. So we now have the kind of basic stuff on digraphs in place, and we're going to look to connectedness. Now, we've just finished a chapter on connectivity for graphs, where we were looking at these kind of high order concepts of connectivity, K-connectedness, but we're going all the way back to the basics, just connectedness. So you remember for a graph, connectedness is all very easy. We have a notion of a walk from U to V. If your graph has the property that for any two vertices U and V, there's a walk from U to V, then your graph is connected. If your graph is not connected, then you have connected components, right? So then your vertices break up into, your graph breaks up into connected components, and the connected components are completely answering the question of when is there a walk from U to V in the graph, right? If you have two vertices in the same connected component, then there's a walk from U to V. If they're in different connected components, then the answer is no. So now we're going to kind of follow exactly the same line, but in this digraph setting. So we're going to introduce a concept of a directed walk. This is going to be like a walk, but we're going to insist that you respect the orientation of the edges. So you're only allowed to take an edge in the forward direction. So that will be our concept of a directed walk. And then we're going to use this to build up an understanding of connectivity. So that's going to be our kind of first step. Let me say already at the start, you can see some differences between graphs and digraphs. For instance, if I have a graph and I give you a walk from U to V, you automatically get a walk from V to U. You just reverse the thing. In digraphs, that's not going to be the case anymore. And kind of as a result of that, this question of when in a digraph is there a walk from U to V, it's actually much more subtle than it is in graphs. So it's not like we're going to get a really simple picture that just comes from connected components. No, it's considerably more involved. But anyway, so I mean this, and actually I should say this is kind of a first indication that some of the stuff that we've done for graphs, when you just kind of take those definitions and carry them over, you have natural terms and natural concepts, but they're leading you to more complicated things than you saw in the undirected setting. So okay, so let's get started with some definitions here. So a directed walk in a digraph D let's say D equals V comma E as before. So this is going to be just as we had for walks. It's a vertex. It's a sequence that alternates between vertices and edges. So I'll start at V0 and then E1 and then V1. And we'll continue on to E sub n and V sub n. And now, what are the rules? Well, each of those V sub i's is a vertex. And, oh, that was my best. So each V sub I is a vertex. This is for I between 0 and n. And each, oh, sorry, that's, that starts at 0. Every VI is a vertex, and every E sub I is an edge. And second, so I mean, this is going to look like walk did in the undirected setting. So in the undirected setting, you insisted that, you're alternating vertex, edge, vertex, edge, vertex, edge. In the undirected setting, you just insist that anytime you look at an edge, the two vertices on either side, those are its ends. Now we're going to ask that, but we're going to ask in addition that you're taking the edge in the right direction, in the forward direction. So we're going to insist that that EI goes from VI minus 1 to VI for every edge here, for every 1 less equal I less equal n. Right, so I don't think that I really need to draw much of a picture here, right? We're going to have a little directed graph. We're going to be taking a walk in it. You're going to start at a vertex, follow along an edge to the next vertex, follow along an edge. And the only rule now that's different from what we had before is that when you're following along those edges, you have to take the edge in the forward direction. So if you want to imagine your graph as a little network, then you're imagining now the direction on the edge. Well, that's telling you that this is a road that you can only take in one direction, right? So when you want to move, you can only move forward along that. And with that understanding, this is really the same thing that we saw before, just now with direction. So this is this directed walk. In this case, we say that this is a walk from V0 to Vn. This walk is going to be called closed if V0 equals n. That's same as the definition that we had before. And also as we had before, if all of the vertices V0 up to Vn, if they're all distinct, if you never repeat a vertex, then we're going to call this directed walk. We will also call it a directed path. So again, we did see this back in the undirected setting. I always pause and make a little spiel or apology for this. So in the undirected setting, the term path really has two definitions. Sometimes we treat a path as a subgraph, right, as a graph on its own. Sometimes we treat it as a sequence, vertex, edge, vertex, edge, vertex, edge. We don't worry too much about that multiply defined object because both of the things are they're inherently the same object. You can just either treat it as a graph or as a sequence, and so you have to kind of interpret from context which one is appropriate, but it doesn't really cause much trouble, and we're going to have exactly the same thing here, and similarly it really doesn't cause us too much trouble. So we've already defined the notion of a directed path as a particular type of digraph. I'm now going to say if you have a directed walk and all the vertices are distinct, then you have a directed path. This walk is a directed path if V0, V1 on up to Vn are distinct. Right. So so just as before, we're doing walks. Now the only new thing is that in our walks in this digraph setting, you have to take edges in the forward direction. If you run around back to where you started, we have a closed walk, and if you never repeat a vertex, we have a directed path. Okay, so that's our basic notion of directed walk. This should be very familiar. It is really just walk now with direction. And what's going to happen here, some things are going to behave kind of like they did in the undirected setting, and some things are going to be more complicated. So we're going to get started here with one proposition that is really the same. Let me just change color for fun here. So an easy fact that we had for walks in a graph is if you have a walk from U to V, then you also have a path from U to V. And that's going to behave just the same for digraphs as it did for graphs. Let's see. So let me get the proposition on the page here. So if there is a directed walk from U to V, then there exists a directed path from U to V. Right, so again, this is just like we saw in graphs. If I promise you the presence of a walk, a directed walk from U to V in a digraph, then you're guaranteed to as well have a directed path. And the proof here is exactly the same as the proof was in the undirected setting, right? as soon as I tell you you have a walk from U to V, okay, so then there are going to be lots and lots of walks from U to V in general. We'd like to somehow select one of those things which is going to be a path. So what, you're not allowed to just ask for a path. That doesn't happen automatically, but we can ask for a walk with an extreme feature. This is called making an extremal choice. And what do we want to do here? Well, this is the same reasoning that we saw in the undirected setting. Again, if you have a walk that's going to repeat vertices, then you're going to be able to shorten it. So the nice way to just sort of select a directed walk that is going to be a directed path is just to choose a shortest one. So let me write a couple words and see the argument go. So let's just choose a shortest walk from U to V. Let's say the walk is V0, E1, V1 on up to EN, VN. So I want to, I want to write my walk like this because I want to grab a hold of these indices. But of course, this is going from U to V. So you have the additional information here that U is V0 and V is V sub N. That's not my best V. Anyway, as I've already sort of gestured the thing that's going to go on here, let me kind of draw a little picture to accompany. Of course, this could be considerably messier, but the idea is still just the same. If you're going to repeat a vertex here in your directed walk, then we can just find a shorter directed walk where we don't spend that time going from a vertex back to itself, right? So we're going to walk from U, but instead of whoa, that was not what I wanted to do. We're going to start our walk at U, but instead of running around in a circle, we're just going to continue on our way. So I'll do my best to get the argument down here on the page. Let's suppose for a contradiction that, say, Vi was equal to Vj, where I is less than j. So suppose for a contradiction that you did repeat a vertex. So I chose a shortest possible directed walk from U to V. Here you handed me the thing. Now I see that there's a repeated vertex, Vi equals Vj. Now I can just make a shorter walk, and I'm just going to write it down here. So what we're going to do is we're going to start off at our walk at the usual start. We're going to walk to Vi. But Vi is also the vertex V sub j. So now instead of continuing on between Vi and Vj, I'm already at V sub j, and so I can follow along edge Ej plus 1 from there and keep going until I get to Vn. This is shorter, and that's a contradiction. And and I've got the picture right there. So again, this can't happen. If you gave me the shortest walk from U to V, it's not possible that there's a repeated vertex, and that means that the shortest walk from U to V is necessarily going to be a directed path. And as I said, this is really just the same as the undirected setting. So this is a thing that's working the same and is really quite simple. Okay, so let's introduce one more definition and get a kind of structural characterization for when we have a for when we have a directed walk from U to V. So we have this notion delta, so this operator delta in an ordinary graph, in an undirected graph, right? So if you give me a graph G and a subset of vertices X, I don't know why I'm gesturing this in space. So here's my graph G, here's the subset of vertices X, here's the complement of X, this set of edges here, this is delta of X. So those are the edges that have one end in X and one end in the complement of X, right? So this is what we have for graphs. For digraphs, of course, now edges can go two different ways. So if I give you a subset of vertices x, and there can be some edges that are sticking out of x to the complement and some that are coming back. So let me draw the picture here. So here's x, here's the complement. Now there are some edges that go like this. This is going to be delta plus of x, and there's some edges that go like this, and this is going to be delta. Maybe I should have done this. I don't know if it's easier or clearer if I do this in a different color. These edges that stick this way, this is delta minus of x. Right, so again, this is just a natural extension of our undirected terminology. So delta is telling us delta of a set of vertices. That's referencing which edges have exactly one end in that set. Now that we're in the digraph setting, we have to worry about directions. So delta plus of x, those are going to be the edges that are sticking out of x. So they're going from x to the complement. Delta minus, those are the edges that are going from the complement of x to x. And with that, we're ready for a very simple but also very important proposition. So I'm going to give you a digraph, and I'm going to give you a pair of vertices. So I've got a digraph, I've got a pair of vertices, and what I'm interested in is, do we have a directed walk from U to V? Right? Certainly a thing that we care about, a thing that we would like to know. Now, here's the story, and this should, well, I don't know, this should feel a little bit like one of these Menger type conditions. The argument is going to be kind of a familiar one when I put it down. So I have a digraph, I have two vertices U and V, then exactly one of the following holds. So either there is a directed walk from U to V, or there's a very good structural reason why not. What would be a structural reason why there's no directed walk from U to V? Let me draw a picture up here. So why would there be no walk from U to V? Well, here's the thing that would really get in your way. Suppose there was a subset of vertices x containing U but not V, and I told you that there are no edges that go from x to the complement. So I don't mind if you have edges going back like this, but I'm telling you that delta plus of x is empty. So there are no edges that go from x to the complement. Well, if there are no edges that go from x to the complement, then if you start a directed walk in x, for instance, if you start a directed walk at the vertex U, you are never going to be able to leave the set x, and that means you are never going to be able to get to the vertex V, because V is in the complement, right? Because if you're taking a directed walk, you can only go forward along directed edges. So if there are no edges that leave the set x, you're never going to be able to get outside of that set, and therefore there would be no directed walk. And in fact, what we have here is yet another one of these very nice kind of structural theorems in graph theory, where either we get the thing that we like, directed walk from U to V, or there's a very obvious structural thing that's preventing the presence of that object. Here, a subset of vertices containing the vertex that you're supposed to start at, but not the one you're headed to, with the property that there are just no edges that are directed out of that set to its complement. So let me write that down. There exists a subset of vertices x such that the vertex U is contained in x. v is not in x, and delta plus of x is empty, right? Again, I'm tasked here with proving that exactly one of these two properties holds, but it's clear that it should be clear that they're mutually exclusive. If you have this second property, there will not be a directed walk from u to v. So all I have to do is, so to complete the proof, I just have to show you that one of these two holds. So let's do that. This is pretty easy. I'm going to define a natural set x. X is going to be what? Well, this is a thing that we saw back in the undirected graph setting sometimes. I'm interested in starting at the vertex u and taking a directed walk that comes out of u. I'm just going to declare x to be the set of all the vertices you can reach. So I'm going to define x to be the set of all vertices, let's say w, such that there exists a directed walk from u to w. Right, so x is all the vertices that you can reach if you start at u and follow along a directed walk. Now, a couple easy properties of one easy property of x is that u must be in x. As in the undirected setting, we have a trivial directed walk consisting only of a single vertex. It's a perfectly valid walk. It's a walk of length 0. It's not a very exciting walk, but it is a walk that goes from any vertex to itself. So in particular, I have a walk that goes from u to u, and that means that my vertex u does lie in the set x. Now, there are two possibilities for the vertex v. Either v lies in x or not. If v is in x, well, just think back to the definition of x. X is the set of all vertices, so there exists a walk from u to that vertex. If v lies in my set x, then there's a walk from u to v. That's what I wanted. So if v lies in x, then 1 holds. And I'm done. Otherwise, what's going to happen? Well, let's think about this set x, right? Sorry, I'm a little bit short on space as always here. So here's the set x. It's containing my vertex u. Here's the complement, v without x, and my vertex v lies over here. Well, I claim that delta plus of x is empty. I claim that there are no edges that go from x to the complement. Why not? Suppose you had an edge like this. Like this. Well, what would that mean? Well, this is some edge in my digraph. So it goes from, let's say it goes from s to t. Now, by my definitions, there must exist a directed walk from the vertex u to the vertex s, because s lies in the set x. I have an edge here that goes from s to t. If you have a directed walk from u to s, you can append this edge and then put the vertex t at the end of this walk, and you now have a directed walk from u to the vertex t. But that's a contradiction because t is not in x, right? T is not in x, and that means there's not supposed to be a directed walk. I mean, that means there does not exist a directed walk from u to t. So again, what we're seeing here quickly is if delta plus of this set x was not empty, you just get a contradiction. Else delta plus of x is empty. Again, there's a little argument there. I'm giving it to you. If delta plus of x was not empty, that would mean there's a vertex s in x and a vertex t in the complement of x and an edge from s to t. And then you'd get a contradiction. Then you'd have a walk from u to s because s lies in the set x. Appending this edge and the vertex t would give you a walk from u to t, and that contradicts the fact that t is not in x. So otherwise, so this can't happen. So this means that, well, if your vertex v is not lying in x, delta plus of x is empty, and that means that 2 holds. So that means that we get our second property here. So so just as we had in a number of kind of connectedness properties from the last chapter, we do have a nice if and only if kind of a characterization of when you have a directed walk from one vertex to another. Again, if I give you 2 vertices u and v, either you get a walk from u to v, or there's a very obvious reason why not. There's a set of vertices that contains u but not v, and there are just no edges out of that set. So if you start at the vertex u and start taking a walk, you're going to stay trapped in that set forever. Okay, so so things are getting a little bit more complicated than graphs, but we are seeing a nice sort of structural characterization. Now let me add one more definition here. So for graphs, we say that a graph is connected if there's a walk between any 2 vertices. We're now going to introduce a digraph version of this that's taking orientations into account, and we're going to call it strongly connected. So a digraph D E is strongly connected if for all vertices u and v there is a directed walk from u to v. Okay, now now what we're going to do is introduce, so we have this notion of strongly connected. And I want to say this is, this is going to be part of our story of connectivity for digraphs, right? So strongly connected digraphs, those are, from a connectivity standpoint, those are very simple. Means for any 2 vertices they give you, there's a walk from one to the other. Now, in the undirected setting, we had the emergence of these components, and they're telling us about connectivity. What we're going to head toward here is a notion of a type of component for digraphs. But I want to warn you again that is going to be a step more complicated. Anyway, let's begin with a simple lemma that we're going to use to kind of tame these things. So I'm going to give you a digraph D, and I'm going to give you 2 subdigraphs, and I'm going to promise you that both of those subdigraphs, I'm not always going to say the die here. The die will have to be implied. But if I give you a digraph and 2 strongly connected subdigraphs, I'll say it sometimes, and those 2 subdigraphs intersect, they share a vertex in common, then I claim that the union of those 2 is still going to be strongly connected. Once again, you could maybe feel that this is similar to something, or maybe remember that this is something similar to what we saw before in the undirected setting. I think you can maybe feel why this is going to be true if you can kind of remember that proof a little bit. Anyway, let's get it on the page. So here, D is going to be a digraph. I'm going to give you H1 and H2. So these are subdigraphs. Again, I'm going to stop saying the subdigraph. Sometimes I'll just say subgraph. And I'm going to insist that H1 and H2 are strongly connected. Right? So again, that means for the digraph H1, for any 2 vertices in H1, there's a directed walk from one to another in H1, and same for H2. And now I'm going to tell you that H1 and H2 share a vertex in common. Or maybe what I'll say is if they share a vertex in common. then H1 union H2 is strongly connected. Okay. Let's prove this guy. So the proof here is going to be just like the one that we had in the undirected setting. Let's well, let me just draw a picture over here. Try and draw a better picture over here. So here's H1 and here's H2, and there must be a vertex, say W, that's common to the two. There it is. There's our vertex W. Now, the easy observation is that for every vertex in H1 union H2, you're going to have a directed walk from that vertex to W, because what? Well, that vertex is either in H1 or it's in H2. If it's in H1, then H1 contains a directed walk from that vertex to W. If it's in H2, fine. Then there's a directed walk in H2 from that vertex to W. Same reasoning, there's a directed walk from W to that vertex. Again, same thing. So I'm going to choose this vertex W. I'm going to let, say, U and V be vertices in H1 union H2. Now, U must be a vertex of HI. Sorry, let me just say choose I equal 1 or 2, such that U is a vertex of HI, and let's similarly choose J equal 1 or 2, such that V is a vertex in HJ. And now what we know is HI has a directed walk from U to W. HJ has a directed walk from W to V. Again, these HI and HJ are strongly connected digraphs. That means you have a directed walk between any pair of vertices. Again, we're just using the obvious fact that W is, because W lies in the intersection, W is in H1 and H2, and that means no matter where U lies or where V lies, I'm going to be allowed a directed walk from U to W or from W to V. So I get a directed walk in HI from U to W, a directed walk in HJ from W to V. These together imply that H1 union H2, just concatenating those two directed walks, H1 union H2 has a directed walk U to V. So that's what I was aiming to prove. So so this is just a simple lemma. This is one that is looking just like what we saw in the graph setting. Again, if you have, the graph setting, if I give you a big graph G and two subgraphs H1 and H2, if H1 is connected and H2 is connected and they overlap, then the union of those two subgraphs is connected. Same story here for digraphs. If I have a big digraph D, I give you two subdigraphs H1 and H2, and I promise you that H1 is strongly connected and H2 is strongly connected, and they share a vertex, then their union is going to be strongly connected. And the proof is really much the same. Now, based on that lemma, we are now going to introduce a very important concept, that of a strong component. Excuse me. So a strong component of a digraph D is a maximal. It's going to be a maximal strongly connected subdigraph. Now, easy fact here, well, based on our lemma, is that in fact every theorem, based on our previous lemma, is that every vertex is in a unique strong component. So this part is looking just like connectedness in undirected graphs, right? So in undirected graphs, we have this notion of component. Every vertex lies in a unique component. So we have the same thing happening here, and it's for exactly the same reasoning. We've just set up our things lining up just as they did before. This is very, very easy to prove. Why? Well, for any vertex, I have a strongly connected subdigraph that consists of that vertex and nothing else, right? No edges. Again, if you take that isolated vertex, that single vertex graph, that graph is going to have the property that for any vertices u and v, there is a directed walk from u to v, because you only have one choice for u and v. It's the same vertex, and you've got the trivial directed walk. So every vertex does lie in some strongly connected subdigraph. But based on the previous lemma, we know that if you have two strongly connected subdigraphs that share your vertex, then their union is going to be another strongly connected subdigraph containing that vertex. So what this means is as soon as you know that every vertex is contained in at least one strongly connected subdigraph, the previous lemma just implies that there's exactly one. So the proof is for every v, there is a strongly connected subdigraph consisting of v. So that means that every vertex is in some strong component. But now, so every vertex is going to be in some strong component, but now just by the previous lemma, if you were to imagine for a contradiction that some vertex lies in more than one strong component, then you have H1 and H2, they're strongly connected subdigraphs. They both have to contain the vertex V, but then their union would be a strongly connected subdigraph containing the vertex V, and it would just be larger than H1 or H2, and that's contradicting maximality. Remember, a strong component, I didn't underline it here, but a strong component, that's what we're defining here, that's a maximal strongly connected subdigraph. So it's got to be strongly connected, and it's got to be maximal. So that means you can't increase it while staying strongly connected. So my proof here, for every vertex V, there's a strongly connected subdigraph consisting of V, so every V is in some strong component. The previous lemma implies exactly one. So there we are. So we do have a notion of a strong component that is going to behave kind of like a component did in undirected graphs, at least in the sense that every vertex is going to be contained in exactly one strong component. Let me go ahead and draw a picture of something here. So here's a digraph D. Let's talk about the strong components. Now, Up at the top here, you see a little directed triangle, right? Now the presence of that directed triangle, it's clear you can take any vertex there in that triangle and get to any other vertex in that triangle, because you can just follow along the orientation of the triangle till you get to the one you want. And in fact, this one is going to be a strong component. Similarly, in the downstairs, you have a directed cycle of length 2. You can get from either of those vertices to the other one. This one is going to as well be a strong component. Why are those two strong components? I mean, why can't you make a bigger graph? Why can't I enlarge them? Well, you can see that we have this, we have a cut here, right? An edge cut. If you, with the property that all of the edges go down, right? So when you look at this, I've partitioned the vertices into two sets, and when I look at the edges in between, they all go down. You don't have any edges going back up. And that's bad news if you were hoping for larger strong components here, right? It means that if you have any vertex in the downstairs, you do not have a directed walk from it to the set upstairs. So what's going on in this digraph? Let's just talk about this digraph relative to presence of directed walks. So what's going on here is I have two sets. Let me call them X and Y. And what's going on just in this particular digraph is for any two vertices in X, there's a directed walk from one to the other. For any two vertices in Y, there's a directed walk from one to the other. If you give me one vertex in X and one in Y, then there's a directed walk from the one in X to the one in Y, but not the other way around, right? So this is getting kind of a little bit more complicated, right? Like, again, in the setting of undirected graphs, when I gave you the connected components, that's just the end of the day for everything you'd want to know about the presence of walks from one vertex to another. We've now defined an analogous concept, which is that of a strong component. So this is going to be a maximal, strongly connected subdigraph. And it is still true that every vertex lies in a unique strong component. But now what's different is that the presence of the partition into strong components does not tell you everything there is to know about the presence of directed walks. Okay, so we're going to unravel that story a little bit further in the next lesson, but that's going to be it for this one.